gazing outward from this tranquil corner where you stand. The twinkling stars in the night sky seem close enough to touch. Yet these gentle points of light actually originate from the distant past. Each beam carries a story spanning time and space. Let us gradually broaden our perspective. First, the blue planet where you reside. Earth appears as a speck of dust in the boundless cosmos. Yet it remains the only known home nurturing life. Departing Earth's surface, we enter the surrounding realm of space, where artificial satellites and the International Space Station represent humanity's initial attempts to explore the cosmos. Continuing our outward journey, we pass the Moon, our closest neighbor, at a distance of approximately 380,000 kilometers, a span large enough to accommodate all other planets in the solar system. Traversing the inner solar system, Mercury, Venus, and Mars successively flash by. These rocky planets share Earth's origins, yet each has followed a distinct evolutionary path. Next come the massive gas giants. Jupiter and Saturn are renowned for their spectacular rings, while Uranus and Neptune orbit farther out, traveling silently along their paths. Crossing the Kuiper Belt where Pluto resides, we reach the solar system's edge. Here, we are approximately 1 solar day's distance from the Sun. Light takes a full day to reach this point, yet the solar system is merely a tiny component within the Milky Way galaxy. Within our galaxy, there are hundreds of billions of stars like our Sun. Together, they form a vast spiral structure. The Milky Way spans approximately 100,000 light-years in diameter. This means traversing the entire galaxy at the speed of light would take 100,000 years. This scale far exceeds human intuitive comprehension. Among all regions of the Milky Way, the most enigmatic is its central zone. Here, stellar density is exceptionally high, and the interstellar environment is extraordinarily complex. Most strikingly, an invisible gravitational source exists here. Through long-term observations, astronomers discovered that all stars in the Milky Way orbit around an invisible central point. This center lies in the direction of Sagittarius, obscured by a thick dust cloud. Through radio and infrared observations, we pierce this dust veil to glimpse the true face of the galactic center. The scene is astonishing. Millions of stars, orbiting an invisible point at astonishing speeds. Their trajectories reveal the presence of an object of immense mass. This invisible celestial object possesses a mass equivalent to 4 million suns, yet is compressed within a relatively small space. Such extreme conditions can only be explained by one entity, a supermassive black hole. This gravitational behemoth, hidden at the Milky Way's core, though it emits no light itself, exerts such powerful gravitational control over the entire galaxy's motion that it dictates the fate of hundreds of billions of stars. It functions like a cosmic clockmaker, silently regulating the rhythms of the Milky Way, maintaining the structural stability of this vast galaxy. So what exactly is this invisible cosmic monster? How did it form? And how does it influence our own galaxy? These questions guide our continued exploration as we seek answers in the journey ahead. In the profound darkness at the Milky Way's heart, an invisible cosmic colossus slumbers silently. Its existence was not initially discovered through direct observation, but revealed through the clues of its immense gravitational influence. This mysterious celestial object, dubbed Sagittarius A by astronomers, resides in the very core of our galaxy, approximately 26,000 light-years from Earth, completely invisible in the visible light spectrum, yet revealed through observations in other wavelengths. Imagine behind a dense curtain of stardust lurks a celestial body of immense mass. equivalent to 4 million suns, yet concentrated within a space smaller than our solar system. This extreme concentration of matter exceeds the physical limits of ordinary celestial bodies. As early as the 1930s, astronomers noted anomalies in the galactic center. The unusually high velocities of stars in that region suggested the presence of a powerful, hidden gravitational source. Like a giant spider lurking at the center of a cosmic web, it controls the entire galaxy through its gravitational threads. Through precise spectroscopic observations, scientists discovered that stars near the galactic center move at astonishing speeds, with orbital velocities exceeding 5,000 kilometers per second for some. Such high-speed motion indicates they are gravitationally bound by a massive celestial object. This hidden colossus, though non-luminous, leaves telltale traces across multiple wavelengths. In the radio spectrum, it emits intense signals. In the X-ray band, it occasionally flashes with brilliance. In the infrared range, it can be indirectly detected. Observational data from these diverse wavelengths converge upon a single conclusion. Calculations reveal the mass density of this invisible object reaches astonishing levels. Such immense mass concentrated within such a small region can only be explained by it being a supermassive black hole. This black hole acts as the heart of the galaxy, using gravity to sustain the entire Milky Way's operation. Even more astonishingly, this cosmic behemoth remains quiet most of the time, existing in a dormant state, yet it occasionally stirs slightly, releasing ripples of energy, like a sleeping giant turning in its dreams. By observing the orbits of stars circling it, astronomers have precisely measured its mass. These stars act as cosmic probes, mapping the invisible contours of gravity with their trajectories, revealing the true nature of this hidden colossus. In our next exploration, we will gradually peel back the veil of mystery surrounding this cosmic monster, from its discovery journey to its peculiar properties, from its impact on the surrounding environment to its role in the cosmos. Each chapter will deepen our understanding of this gravitational colossus that governs our Milky Way galaxy. Now, let us maintain this state of relaxation as we prepare to enter the next phase of exploration. On this tranquil night, engage in a conversation across time and space with this distant cosmic neighbor. Reflections on the nature of gravity. This journey traces back to the era of Isaac Newton. His law of universal gravitation, proposed in the 17th century, successfully explained the patterns of planetary motion around the sun. Newton described gravity as an instantaneous action-at-a-distance force, believing masses attract each other. Yet this theory struggled to explain certain phenomena, such as the precession of Mercury's perihelion. It wasn't until the early 20th century that Albert Einstein introduced a revolutionary theory. General relativity fundamentally transformed our understanding of gravity. In this theory, gravity is no longer an attractive force between objects, but rather the effect of mass warping spacetime. Imagine spacetime as a stretched rubber sheet. Placing a heavy object causes the sheet to dent. Smaller objects then move along this curved surface. This geometric effect is what we perceive as gravity. Based on the field equations of general relativity, Carl Schwarzschild found an exact solution in 1916. This solution describes an ideal celestial body, with spherical symmetry, and no charge or angular momentum, the structure of spacetime around it. The Schwarzschild solution predicts the existence of a critical radius. Within this radius, the curvature of spacetime becomes so extreme that no matter or radiation can escape. This is the concept of the event horizon. The event horizon is not a physical boundary. but a one-way membrane in spacetime. Objects can cross the event horizon into the black hole, but nothing can return from it. It is akin to a river in the cosmos, reaching a point where it plunges vertically like a waterfall. Within the edge of this waterfall, all paths lead downward. The size of the event horizon is proportional to the black hole's mass. For a black hole with the mass of the Sun, its Schwarzschild radius is approximately 3 kilometers. At the center of the event horizon, general relativity predicts the existence of a singularity. At this point, space-time curvature approaches infinity. All known physical laws cease to apply. Density and temperature reach infinite values. The singularity can be considered the frontier of theoretical physics, serving as a reminder that general relativity requires modification under extreme conditions, potentially necessitating the introduction of quantum gravity theory. It is crucial to emphasize that black holes are not cosmic vacuum cleaners, actively devouring distant objects. The gravitational influence of a black hole is identical to that of an object of equal mass. If you replace the black hole with an ordinary star of the same mass, in regions far from them, the gravitational effects are completely identical. Only when extremely close to the black hole do its unique properties manifest. The gravitational field of a black hole follows the inverse square law. Just like any other object with mass, at sufficiently distant ranges, celestial bodies orbiting a black hole can maintain stable orbits, much like planets circling a star. Only when an object comes too close to the event horizon will it be captured by the black hole's immense gravitational pull. This misconception likely stems from the mysterious nature of black holes, specifically their property of preventing any light from escaping, rendering them invisible to direct observation. In reality, black holes are simply celestial bodies in the universe possessing immense gravitational pull. Their uniqueness lies in their extreme concentration of matter, rather than possessing some supernatural suction force. By observing the effects black holes exert on their surroundings, we can indirectly study these enigmatic celestial bodies, such as tracking the motion of stars around the invisible center of the Milky Way, or analyzing radiation emitted by accretion disks. These observations confirm the fundamental nature of black holes as gravitational entities. Understanding the true nature of black holes is crucial to our comprehension of the universe. These cosmic gravitational behemoths, though seemingly terrifying, actually follow the same physical laws of gravity. Under the same physical laws, only exhibiting their most extreme manifestations, under extreme conditions. With advances in observational technology, we are gradually unveiling the veil of mystery surrounding black holes. From theoretical predictions to actual observations, these cosmic entities are revealing to us the most extreme gravitational environments in nature. In the exploration ahead, we will witness how these black holes shape the structure of the universe and their pivotal role in galactic evolution. The motion of stars within the Milky Way follows specific patterns. These patterns were initially revealed by observing the trajectories of numerous stars. Astronomers discovered that stars in the Milky Way do not move randomly. Instead, they exhibit organized rotational patterns. Stars at different distances from the galactic center exhibit systematic differences in their velocities. Through precise spectroscopic observations, scientists measured the radial velocities of thousands of stars, combined with data on proper motion, to construct the Milky Way's rotation curve. This curve describes how stellar rotational speeds around the galactic center vary with distance, according to Kepler's laws of motion, under the influence of central gravitational forces. The orbital velocity of celestial bodies should decrease with increasing distance, much like the motion of planets in our solar system. Yet actual observations present a puzzle. In the outer regions of the Milky Way, stellar rotational speeds do not decrease as expected. Instead, they maintain a consistently high value. This phenomenon severely contradicts predictions based on the distribution of visible matter, suggesting the presence of some unknown factor. Further research indicates that gravitational forces from visible matter alone are insufficient to maintain the structural stability of the Milky Way. Calculations of the total mass from all visible matter, including stars, interstellar gas, and dust, the gravitational effect produced by the total mass, falls far short of explaining the observed stellar velocities. The distribution of visible matter in the Milky Way is primarily concentrated in the galactic disk and bulge regions. Beyond these areas, mass density drops sharply. Yet, the high-velocity motion of stars indicates a powerful gravitational field persists in the outer regions of the galaxy. This gravity must be supplied by an additional source of mass. Through dynamical modeling, astronomers calculated the mass distribution required to maintain the Milky Way's rotation curve. This model reveals the existence of vast quantities of invisible matter, not only distributed in the galaxy's outer regions, but also forming a nearly spherical halo structure. This invisible substance is termed dark matter. It does not interact with electromagnetic waves, and thus cannot be directly observed through telescopes. However, its gravitational effects are undeniably present in galactic motions. Dark matter constitutes the primary component of the Milky Way's mass, with its total quantity estimated to be 5 to 6 times that of visible matter. In the central region of the Milky Way, gravitational anomalies are particularly pronounced. Here, stellar velocities are exceptionally high, with some stars orbiting at speeds exceeding 500 kilometers per second. Such extreme velocities imply a tremendous mass is concentrated within an extremely small spatial range at the galactic center. Take the specific star S2 at the galactic center as an example. Its motion follows an extremely elliptical orbit, with its closest approach to the center being only 120 astronomical units. At this position, its velocity reaches 3% of the speed of light. Such a high-speed state of motion reveals the powerful gravitational pull of the central source. By precisely measuring the orbital parameters of these stars and applying Kepler's third law for calculation, scientists concluded that a celestial body of immense mass and minuscule volume exists at the galactic center. This object possesses a mass approximately 4 million times that of the Sun, while its radius does not exceed the orbital radius of Mercury. Such extreme mass density rules out the possibility of ordinary stellar clusters or groups. Even the densest neutron star clusters could not contain such immense mass within such a small space. The only plausible explanation is the presence of a supermassive black hole. This hidden mass source acts like an invisible gravitational engine. Through its powerful gravitational field, it governs the entire dynamical structure of the Milky Way. It not only influences the motion of nearby stars, but also, through gravitational effects, shapes the large-scale structure of the Milky Way. The stellar distribution in the galactic center exhibits a distinct bulge structure. The formation and maintenance of this structure are both closely tied to the gravitational influence of the central supermassive black hole. The black hole's gravity affects star formation and evolution, and regulates the dynamical environment of the galactic nucleus. From a broader perspective, this hidden mass source at the galactic center acts as a gravitational anchor for the entire galaxy. maintaining the stability of the spiral arm structure, influencing the dynamical evolution of the galactic bar, and co-evolving with the galaxy through gravitational interactions. This discovery not only transforms our understanding of the Milky Way's structure, but also provides crucial insights into galaxy formation and evolution. In modern astrophysics, the coevolution of supermassive black holes and their host galaxies has become a major field of research. Through continuous observations of stellar motions around the galactic center, scientists are progressively refining measurements of the central black hole's parameters. These observational data not only validate predictions of general relativity, but also provide a valuable experimental arena for understanding physical laws in extreme gravitational environments. The gravitational anomaly at the Milky Way's center is a vital revelation from the cosmos. It informs us that the universe contains vast quantities of invisible matter and energy. Though unobservable directly, these forces interact gravitationally to shape the cosmic structures we perceive. This discovery reminds us that human understanding remains limited. Countless unknowns in the universe await our exploration. Each advancement in observational technology holds the potential for new discoveries and breakthroughs in our knowledge. Visible light traversing the galactic plane encounters vast quantities of interstellar dust particles. These minute solid particles are widely dispersed throughout interstellar space and cause severe scattering and absorption of visible light. This prevents optical telescopes from directly observing the true conditions at the galactic center. The obscuring effect of interstellar dust is like a persistent cosmic fog, hiding the galactic core from view. Astronomers estimate that in the visible light spectrum, the brightness of the galactic center is attenuated by billions of times. This makes optical research nearly impossible. Yet nature has opened another window for us. Electromagnetic radiation in the radio wavelength band possesses significantly longer wavelengths, typically ranging from millimeters to meters. Photons at these wavelengths interact weakly with interstellar dust particles and can traverse dust clouds with minimal attenuation. Much like radio signals penetrate walls, radio waves can penetrate interstellar medium hundreds of light years thick. In the 1930s, Carl Jansky, while investigating radio communication interference, accidentally discovered radio emissions from the galactic center. This serendipitous finding marked the birth of radio astronomy. Over the following decades, radio telescope technology advanced rapidly. The year 1974 stands as a pivotal milestone in astronomical history. Astronomers Bruce Barrick and Robert Brown utilized the National Radio Astronomy Observatory's interferometer to conduct high-resolution observations of the galactic center. They identified an exceptionally dense and luminous radio source, positioned at the galactic dynamical center, designated Sagittarius A star. The significance of this discovery lies in its fulfillment of a crucial criterion. For candidates of the galactic center, the radio source must reside at the precise dynamical center of the Milky Way, the intersection of the galactic rotation axis, and the focal point around which all stars and gas orbit. The radio properties of Sagittarius A* are highly distinctive. As a non-thermal radiation source, meaning its radiation mechanism differs from the thermal emission of ordinary stars. This radiation is typically associated with synchrotron radiation from relativistic electrons. When electrons spiral along helical trajectories within intense magnetic fields, they emit this characteristic polarized radiation. Observational data indicate Sagittarius A* is an extremely compact source. With an angular diameter less than 1 arcsecond, corresponding to an actual diameter not exceeding 1 astronomical unit. Such a small size producing such intense radio emission indicates extremely high energy density within it, compared to other known radio sources. Sagittarius A* exhibits exceptionally stable radiation characteristics. Its luminosity remains relatively constant over decades, without significant fluctuations. This stability suggests the presence of a massive, stable energy source. Further research reveals Sagittarius A* actually consists of multiple components, including an extended radio structure and an extremely compact core. This core component is the celestial body later designated Sagittarius A star. It is recognized as the direct counterpart to a supermassive black hole. Radio observations also reveal Sagittarius A* exhibits distinctive spectral characteristics. Its radiation intensity varies with frequency in a specific distribution pattern. This spectral distribution cannot be explained by conventional stellar radiation mechanisms, but aligns with models involving accretion disks or relativistic jets. Notably, Sagittarius A* exhibits partially polarized radiation, indicating the presence of organized magnetic field structures within the emitting region. Magnetic fields play a crucial role in black hole accretion processes, by helping extract energy from the rotating black hole and guiding matter into outflowing jets. Through very long baseline interferometry, astronomers have studied this source at unprecedented resolution. This technique links radio telescopes distributed globally to form a virtual telescope with an equivalent aperture of thousands of kilometers, capable of resolving Sagittarius A*'s fine structure. These observations confirm Sagittarius A** as the densest and brightest radio source at the galactic center, its position precisely coinciding with the galactic dynamical center. Its properties fully consistent with theoretical predictions for supermassive black holes. This groundbreaking discovery in radio astronomy not only reveals the true nature of the Milky Way center, but also provides a model for studying the cores of other galaxies. Today we know that most galactic centers likely harbor similar compact radio sources, which are almost certainly supermassive black holes concealed behind dust. The story of Sagittarius A*''s discovery teaches us that cosmic mysteries often lie hidden in invisible wavelengths. Only through multi-wavelength collaborative observations can we piece together a complete cosmic picture. As a vital tool for probing the depths of the universe, radio astronomy will continue to unveil more cosmic wonders. Modern astronomy has entered the multi-messenger era. We no longer confine our cosmic investigations to a single wavelength. Instead, by combining electromagnetic radiation across different bands, combined with other messengers like gravitational waves and cosmic rays, to build a comprehensive understanding of celestial objects. For Sagittarius A**, the center of our Milky Way galaxy, multi-messenger observations are particularly crucial, as it lies hidden behind a thick dust cloud. The infrared wavelength band is a powerful tool for studying the galactic center. Infrared light has a longer wavelength than visible light, enabling it to penetrate the obstruction of interstellar dust. Much like night vision goggles pierce through mist, infrared telescopes thus offer a glimpse into the galactic center's landscape. Astronomers employ large infrared telescopes, such as the European Southern Observatory's Very Large Telescope, to continuously monitor stellar motion within the galactic center region. By precisely measuring these stars' positions and velocities, they uncovered a remarkable phenomenon: multiple stars orbiting an invisible point at high speeds. The most famous among them is the S2 star. Its orbital period is a mere 16 years. At its closest approach, It comes within just 120 astronomical units of the center. The speed reaches 3% of the speed of light. Such extreme orbital motion can only be explained by the gravitational pull of a supermassive black hole. Infrared observations not only reveal stellar motion, but also help us measure the black hole's parameters. By analyzing these stars' orbits, astronomers precisely calculated the central black hole's mass at 4.3 million solar masses, with an astonishing measurement accuracy of 0.1%. Beyond studying stellar motion, infrared observations also reveal the environment surrounding the black hole. We observe dense star clusters, young massive stars, and gas clouds warped by the black hole's gravity. These observations provide invaluable data for understanding the extreme conditions at the Milky Way's center. When we shift our gaze to the X-ray spectrum, a different picture emerges. X-rays are extremely high-energy photons, typically emitted by gas heated to millions of degrees, or by relativistic particles. Observations from the Chandra X-ray Observatory reveal faint X-ray radiation around Sagittarius A*, originating from the innermost region of the black hole's accretion disk, where temperatures reach tens of millions of degrees. As gas spirals into the black hole, gravitational energy is converted into thermal and radiative energy. Occasionally, we observe X-ray flares, lasting from tens of minutes to several hours, with brightness increasing by a factor of several to dozens. Astronomers believe these flares may originate from magnetic reconnection processes or clumps of matter falling into the black hole. Even more intriguing is the detection of X-ray echoes within the molecular cloud surrounding the black hole. These echoes reveal that Sagittarius A* underwent an active phase hundreds of years ago, when its luminosity was millions of times greater than today. By analyzing the energy spectrum and temporal variations of X-ray radiation, we can study extreme physical processes near black holes, including the behavior of matter in strong gravitational fields, the effects of relativistic phenomena, the details of the accretion process. The radio wavelength provides opportunities to study black hole jets and magnetic fields. The Event Horizon Telescope successfully captured the shadow image of a black hole in the radio band, marking humanity's first direct glimpse of a black hole's outline. Observations across different wavelengths are not independent, but complementary. Infrared data reveals how stars move. X-ray data reveals the properties of high-temperature matter. Radio data reveals large-scale structures and magnetic fields. Only by combining this information can we fully understand black hole behavior. For example, in a multi-wavelength joint observation, astronomers simultaneously used infrared, X-ray, and radio telescopes to monitor Sagittarius A* activity. They discovered that when X-ray flares occur, corresponding changes also appear in the infrared and radio bands. This indicates that radiation across different wavelengths may originate from related physical processes. The strength of multi-messenger astronomy lies in its ability to overcome the limitations of single-wavelength observations by providing opportunities for cross-validation. If a model can simultaneously explain observations across all wavelengths, we gain greater confidence that it reflects reality. For Sagittarius A*, multi-wavelength observations confirm it is indeed a massive yet relatively quiescent black hole. Its quiet state may be temporary. On cosmic timescales, could reawaken and exhibit violent, quasar-like activity. Future telescopes and observational techniques will further enhance our ability to study the galactic center. The James Webb Space Telescope will deliver more precise infrared observations, Next-generation X-ray telescopes will reveal fainter radiation signatures. More sensitive radio telescope arrays will provide higher resolution images. Multi-messenger astronomy is transforming our understanding of the galactic center. Each new observation paints a more complete picture, gradually unveiling the mysteries of this cosmic monster and revealing its role in galaxy evolution and the physical laws governing extreme gravitational environments. Amid the dense stellar field at the Milky Way center lies a unique star named S2. Its orbital path confirms the presence of a central black hole. S2 possesses approximately 15 times the Sun's mass and far outshines our star, enabling clear tracking of its motion from 26,000 light-years away. Astronomers have conducted continuous observations of S2 for over 2 decades using the Very Large Telescope at the European Southern Observatory. Employing adaptive optics technology to correct atmospheric disturbances, they achieved astonishing measurement precision. Positional accuracy reached tens of microarcseconds, equivalent to seeing a coin on the moon from Earth. S2 orbits in a highly elliptical path, with an eccentricity of 0.88. Its orbital period is 16.05 years. At its closest approach, it reaches just 120 astronomical units from the center. At its farthest, it extends to 970 astronomical units. This extreme orbit creates unique experimental conditions. During its closest approaches in 2002 and 2018, S2 reached astonishing speeds of approximately 17 million miles per hour, equivalent to 2.7% of the speed of light. Such high-speed motion produces pronounced relativistic effects. According to Kepler's third law, the square of the orbital period is proportional to the cube of the semi-major axis. This relationship enables precise calculation of the central body's mass. The formula is T superscript 2 equals 4 pi superscript 2a superscript 3/gm, where T is the orbital period, A is the semi-major axis, G is the gravitational constant, and m is the mass of the central body. Substituting S2's observational data into the formula, the orbital period T is 16.05 years. The semi-major axis A is 5.5 milliarcseconds. Combined with our known distance to the galactic center, 26,000 light-years, we can calculate the mass of the central body. The calculation reveals this invisible object has a mass of 4.3 million solar masses, with an error margin of only 0.1%. Such precise measurements are extremely rare in astrophysics. More significantly, by analyzing the closest approach distance of S2 star, we can constrain the size of the central object. At its closest point, S2 star passed within just 120 astronomical units of the central mass, yet experienced no collision or significant deceleration. This indicates the central object must be considerably smaller than this distance. Actual calculations show the central object's radius must be less than 120 Australian dollars. Otherwise, S2 would have impacted its surface. Compressing such immense mass into such a small volume can only be explained by a black hole. S2's orbital motion also exhibits other relativistic effects, including gravitational redshift and orbital precession. As the star approaches the black hole, its spectral lines shift toward the red end, because photons expend energy escaping the intense gravitational field. The observed gravitational redshift perfectly matches the predictions of general relativity. This further confirms the extreme gravitational nature of the central object. Orbital precession provides another crucial piece of evidence. The elliptical orbit of S2 is not fixed, but slowly rotates in space. With each completed orbit, the direction of its periastron shifts by approximately 12 arc minutes. This observation also aligns with Einstein's predictions. Beyond S2, astronomers have tracked the motions of dozens of other stars, all orbiting the same invisible point. These stars possess distinct orbital characteristics, yet all point toward the same mass center. This eliminates alternative possibilities, such as dense star clusters or peculiar matter formations. All stellar orbits adhere to Kepler's laws, indicating they are governed by the gravitational pull of a single point-like mass. If the center were an extended mass distribution, we would observe distinct orbital characteristics. Stellar orbital dynamics provide the most direct evidence for the existence of a supermassive black hole at the Milky Way's center. This evidence relies on no hypothetical radiation mechanisms, but solely on Newtonian and Einsteinian gravitational theory. These theories have been validated by countless experiments. Through continuous monitoring of these stellar motions, astronomers are steadily refining measurement precision. Future 30-meter class telescopes will enhance mass measurement accuracy by an order of magnitude. Stellar orbital dynamics not only confirms black hole existence, but also provides a laboratory for studying strong gravitational fields. During the 2018 closest approach of S2 stars, multiple observatories conducted joint observations, yielding unprecedented data quality. These observations are helping physicists test the limits of general relativity, search for potential deviations from the standard theory, and explore new physics beyond Einstein's framework. The study of stellar motion around the galactic center stands as a landmark achievement in modern astrophysics. It demonstrates how humanity, through precise measurements and rigorous reasoning, has uncovered the existence of the universe's most enigmatic celestial objects. This discovery will forever alter our understanding of the cosmos. Very Long Baseline Interferometry, VLBI, represents a revolutionary observational technique. By combining radio telescopes distributed across the globe, it creates a virtual telescope with an effective aperture equivalent to Earth's diameter. This technology achieves extremely high angular resolution, sufficient to distinguish an orange on the Moon's surface, or the event horizon of a black hole tens of thousands of light-years away. The principle behind this technology is based on the phenomenon of wave interference. When radio waves from the same source reach telescopes at different locations, phase differences arise due to variations in their propagation paths. By precisely recording the arrival times of signals received by each telescope and correlating this data, the fine structure of celestial objects can be reconstructed. It's like assembling a giant mirror from countless small mirrors. The Event Horizon Telescope project began in 2006 as an international scientific collaboration, uniting over 80 research institutions worldwide and more than 300 scientists, utilizing 8 radio observatories distributed across the globe, including the Atacama Large Millimeter/Submillimeter Array in Chile, the James Clerk Maxwell Telescope in Hawaii, and the South Pole Telescope in Antarctica. The strategic placement of these observatories. They are distributed across different latitudes, longitudes, and elevations, maximizing the baseline length of the virtual telescope. High-altitude sites minimize absorption by atmospheric water vapor, while polar sites offer unique observational perspectives. The entire network operates synergistically, equivalent to a giant telescope with a 10,000-kilometer aperture. From April 5th to 11th, 2017, the EHT organized a joint observation of Sagittarius A star. All participating sites employed hydrogen atomic clocks for time synchronization, ensuring nanosecond-level precision in data recording. Observations centered around the 230 GHz frequency band, which effectively penetrates interstellar medium. while delivering sufficient resolution. Weather conditions during the observation period were critical, requiring clear, dry skies simultaneously across all sites, an opportunity occurring only a few days annually. Scientists prepared months in advance. During this precious observation window, they collected several petabytes of raw data. Data was recorded on specialized high-speed hard drives. Each telescope generated approximately 1 petabyte of data per night. These hard drives were physically transported to processing centers, as network transmission of such massive data volumes proved prohibitively expensive. The Max Planck Institute for Radio Astronomy and the MIT Haystack Observatory served as the two primary data correlation processing centers. The first step in data processing is time alignment. Using atomic clock timestamps from each site, they correct for effects caused by Earth's rotation and atmospheric delays. Then, using specialized supercomputers, they perform cross-correlation processing to find correlations between signals from different telescopes. This process requires extremely high computational precision. The raw data is saturated with various types of noise, including instrumental noise, atmospheric disturbances, and interstellar scattering effects. Scientists developed complex algorithms to filter out these interferences, particularly the impact of interstellar scattering, which blurs images as if viewed through frosted glass. Since the EHT does not continuously cover all spatial frequencies, reconstructing the image presents a massive mathematical challenge. The research team developed 4 independent imaging methods, including the clean algorithm and regularized maximum likelihood. Cross-validation ensured the reliability of the results. To avoid human bias, the team first divided the process data into 4 independent groups, each applying different methods, with results compared only at the final stage. Excitingly, all methods produced similar images. On May 12, 2022, the EHT collaboration released its historic findings. The first image of Sagittarius A** revealed a bright ring-like structure encircling a central dark region, with a diameter of approximately 50 microarcseconds, perfectly matching the shadow size predicted by general relativity. The luminous ring exhibits asymmetry, with the southwest side brighter than the northeast. This asymmetry stems from relativistic beam steering effects. When matter orbits a black hole at speeds approaching light, radiation facing us intensifies, while radiation away from us weakens. The central dark region is the black hole's shadow. It is not the event horizon itself, but rather the silhouette of the event horizon projected against the luminous background. Its size is approximately 2.5 times the diameter of the event horizon. This magnification effect stems from gravitational lensing. The shadow's near-circular shape indicates the black hole's spin axis is roughly aligned with Earth's direction. Through detailed analysis of the shadow's shape and size, scientists further confirmed the black hole's mass and spin. This photograph provides multiple crucial verifications. First, it confirms the existence of the black hole, demonstrating that the event horizon indeed casts a shadow against the luminous background as predicted by theory. Second, it validates general relativity, confirming its predictions remain accurate. In strong gravitational fields, the shadow's precise size corresponds to 4.3 million solar masses. This establishes a solid foundation for black hole astronomy. Conclusions drawn from different methods corroborate each other, enhancing the reliability of the results. The image also reveals the black hole's accretion process. The luminous ring corresponds to hot material surrounding the black hole. This material is heated to billions of degrees before falling into the black hole, emitting intense synchrotron radiation. Bright spots on the ring may correspond to hot spots generated by magnetohydrodynamic instabilities. The EHT's achievement ushers in a new era of black hole research. As more telescopes join the network in the future, with expanded observation frequencies and improved algorithms, we will be able to capture dynamic movies of black holes, observing matter's motion within extreme gravitational fields. This technology will also be applied to studying black holes in other galaxies, particularly the more massive black hole in the Messier 87 galaxy. By comparing the shadows of black holes of different masses, we can test the no-hair theorem for black holes and explore the universality of gravitational theories. The success of the Event Horizon Telescope demonstrates the power of global scientific collaboration. It represents not only a technological breakthrough, but also an expansion of humanity's cognitive frontiers. For the first time, we have directly witnessed the true form of the universe's most enigmatic celestial object. This photograph will be enshrined in the annals of science. It embodies the pinnacle of human intellectual achievement, while reminding us that countless mysteries in the cosmos await our discovery and exploration. The mass of Sagittarius A* has been precisely measured at 4.3 million solar masses. This figure may seem abstract, yet it carries profound physical significance. It means this invisible celestial body possesses a mass equivalent to 4 million times the combined mass of all planets and stars in our solar system. Such immense mass concentrated within an extremely small region creates the most extreme gravitational environment in the cosmos. At this mass scale, effects of general relativity become paramount. Newtonian mechanics can no longer accurately describe the physical processes around it. Through stellar orbital dynamics measurements, the precision of this mass value reached an astonishing 0.1%. This means our understanding of the black hole's mass exceeds the precision of mass measurements for many nearby stars. Such accuracy is exceptionally rare in astrophysics. The size of a black hole's event horizon is directly proportional to its mass. Using the Schwarzschild radius formula, R_s equals 2gm/c superscript 2, we can calculate the event horizon radius of Sagittarius A*, to be approximately 0.08 astronomical units, equivalent to 17 times the radius of the Sun. This scale is minuscule on cosmic terms, equivalent to just 1/5 of Mercury's orbital radius. Imagine compressing the mass of 4.3 million suns into a space smaller than our inner solar system. Such material density defies human intuitive comprehension. The event horizon is not a physical surface, but a critical boundary in spacetime. Beyond this boundary, escape velocity exceeds the speed of light. No matter or information can escape. This boundary defines the fundamental size of a black hole. Beyond mass, the black hole spin is another critical parameter. Spin describes the rotational state of a black hole, originating from the conservation of angular momentum during its formation. For Sagittarius A*, measuring the spin parameter is relatively complex. However, recent observations have provided some clues. By analyzing the motion of matter around the black hole and data from the Event Horizon Telescope, scientists estimate Sagittarius A* exhibits moderate spin, with a spin parameter of between approximately 0.5 and 0.9. This value indicates the black hole is rotating at a fairly rapid pace. A black hole spin induces a dragging effect on the surrounding spacetime, a phenomenon known as frame dragging. Near a rapidly spinning black hole, spacetime itself is dragged along in its rotation. Much like a spoon stirring syrup, spin also affects the size and shape of the event horizon. For a black hole of given mass, the faster it spins, the smaller its event horizon becomes. At maximum spin, the event horizon radius is only half that of a non-spinning black hole. Observations from the Event Horizon Telescope provide new evidence for spin measurements, the asymmetry of the black hole's shadow in the image, and the brightness distribution of the luminous ring. Both contain information about the black hole's spin. These data require complex models for interpretation. Compared to supermassive black holes in other galaxies, Sagittarius A* exhibits both typical and unique properties. In terms of mass, it falls within the lower middle range. The central black holes of many galaxies can reach billions of times the mass of the Sun. For example, the black hole in Messier 87 has a mass of 6.5 billion solar masses, over 1,500 times larger than Sagittarius A*. However, by cosmic standards, 4.3 million solar masses is actually quite typical. The central black holes in most galaxies range from millions to tens of millions of solar masses. Sagittarius A* is unique for its extremely low activity. Despite its immense mass, its radiative luminosity is exceptionally faint, only 1/1,000,000th of the Eddington limit, which represents the maximum theoretical brightness a black hole can achieve. This low activity state may stem from insufficient material supply, as the central region of the Milky Way has relatively low matter density, preventing the black hole from acquiring enough material to sustain high luminosity. Alternatively, it could be due to its current quiet phase within its activity cycle. Compared to active quasars, Sagittarius A* resembles a slumbering giant. Quasars are the brightest objects in the universe, with central black holes rapidly accreting matter and shining thousands of times brighter than entire galaxies. Another defining feature of Sagittarius A* is its relatively close proximity. As the nearest supermassive black hole to Earth, it offers a unique laboratory for studying such celestial bodies. In other galaxies, due to their vast distances, we cannot discern details near the black hole. This proximity allows us to study the black hole's dynamical effects on surrounding stars, observe the detailed process of matter falling into the black hole, and even detect faint temporal variations. Research of this kind is impossible in distant galaxies. Black hole mass is closely linked to the properties of its host galaxy. This is the famous M-sigma relation. The black hole's mass correlates with the velocity dispersion of the galactic bulge. The mass of Sagittarius A* precisely fits this relationship, indicating a shared evolutionary history with black holes in other galaxies. By studying the fundamental parameters of Sagittarius A*, we not only gain insights into this specific object, but also deepen our universal understanding of black hole physics. Its mass and spin state provide crucial observational constraints for theoretical research. With future advances in observational technology, we will achieve more precise measurements of these parameters, particularly the precise determination of spin, which will aid our understanding of black hole formation mechanisms and their coevolution with galaxies. Each precise measurement of these parameters represents a step forward in humanity's comprehension of extreme physics. Through this invisible cosmic monster, we are unveiling nature's deepest mysteries. On cosmic scales, Sagittarius A* exhibits surprisingly mild behavior relative to its immense mass. Its luminosity is only about 1/1,000,000th of the Eddington limit. The Eddington limit represents the maximum theoretical radiation brightness, achievable when matter falls into a black hole under gravitational influence. This remarkably low radiation efficiency reveals the complexity of black hole accretion processes. In the classical thin disk accretion model, matter should spiral into the black hole in an orderly manner, releasing substantial gravitational energy. However, Observations indicate Sagittarius A** has an extremely low actual accretion rate. One primary cause of this low luminosity is insufficient material supply. The interstellar matter density in the galactic center is relatively low. The black hole cannot obtain a sustained and abundant fuel supply. Even when stars or gas clouds approach the black hole, they often do not directly fall into the event horizon, but instead form eccentric orbits. Another key factor is the inefficiency of the accretion process. Only a very small fraction of the accreted material ultimately crosses the event horizon and is swallowed by the black hole. Studies suggest that perhaps only about 1% of the material actually completes the journey from the accretion disk to the black hole. Most of the material is rejected into interstellar space through outflows and jets during the accretion process. This outflow mechanism may be driven by multiple factors, including radiation pressure, magnetohydrodynamic processes, and thermal instabilities. As matter approaches the black hole, it first forms a rotating accretion disk. At different radii within the accretion disk, matter rotates at varying angular velocities, generating intense shear forces and amplified magnetic fields. The amplified magnetic field extracts rotational energy from the black hole, and, through the Branford-Ziniak process, generates relativistic jets. These jets carry vast amounts of matter and energy away from the vicinity of the black hole, reducing the total mass ultimately accreted by the black hole. Thermal instability also plays a crucial role in accretion. Gas within the accretion disk may exist in two distinct states: a low-density, high-temperature state and a high-density, low-temperature state. Transitions between these states can cause dramatic fluctuations in the accretion rate. In the case of Sagittarius A*, the accretion disk likely spends most of its time in the low-density state. Under these conditions, gas cooling is inefficient, preventing effective loss of angular momentum, and thus hindering rapid material flow toward the black hole. Radiative feedback constitutes another crucial mechanism. When accreting matter emits radiation, this radiation exerts pressure on subsequent accretion flows. At low accretion rates, radiative pressure may be insufficient to drive robust outflows, yet it still influences the trajectory of gas motion. The gravitational field characteristics of the black hole itself also influence the accretion process. Within strong gravitational fields, matter must lose substantial angular momentum to migrate from larger orbital radii toward the vicinity of the event horizon. This angular momentum transfer process is often inefficient. The environmental characteristics of the interstellar medium are equally significant. Interstellar gas in the galactic center exhibits high temperatures and low densities. This hot, low-density environment is unfavorable for sustaining stable cold accretion flows. Observational data indicate that Sagittarius A* accretes approximately 10 solar masses per year. This rate implies it would require billions of years to achieve significant mass growth. Given its current accretion efficiency, its growth pace is exceptionally slow. This mild accretion behavior keeps Sagittarius A* in a relatively quiescent state for most of its existence. Compared to quasars in active galactic nuclei, its radiation intensity is negligible. However, this quiet state may be temporary. When large gas clouds or stars accidentally approach the black hole, it may trigger brief brightening events, such as the X-ray echo observed in the 19th century, and the infrared flare in 2019. These occasional bursts of activity remind us that this seemingly docile cosmic beast still possesses latent energy, though currently lacking sufficient fuel supply. Understanding Sagittarius A*'s mild temperament not only helps us comprehend the behavior of this specific black hole, but also provides a crucial reference case for studying low-luminosity active galactic nuclei in other galaxies. On a broader cosmological scale, this inefficient accretion process may represent the typical state of most supermassive black holes during the majority of the universe's history, rather than the extreme activity seen in quasars. By studying Sagittarius A**'S accretion process, we gain insights into the complex interactions between black holes and their surroundings. These interactions not only determine the black hole's own evolution, but also influence the energy cycling of entire galactic ecosystems. With continuous advancements in observational technology, we will be able to study the dietary habits of this cosmic behemoth in greater detail, unveiling more mysteries about how matter behaves in extreme gravitational fields. Beneath the tranquil night sky, this distant cosmic neighbor continues in its own unique way to narrate the story of gravity to us. Approximately 2 centuries ago, the colossal beast at our Milky Way's core underwent an unusual period of activity. This event was not directly recorded by astronomers of the time, but was detected in the present through its cosmic echoes. When astronomers used the Chandra X-ray Observatory to observe molecular clouds in the galactic center, they discovered these gas clouds, which should have been dark and cold, were emitting anomalous X-ray radiation. These emissions exhibited specific spectral characteristics, indicating they were not self-luminous, but rather reflecting X-rays from elsewhere. By analyzing the propagation paths and timing of these reflected signals, scientists traced them back to a startling conclusion. These molecular clouds were reflecting X-ray radiation released by Sagittarius A**. Approximately 200 years ago, this outburst amplified the black hole's X-ray luminosity. This historic outburst persisted for several years, with peak luminosity approaching the Eddington limit, indicating the black hole underwent an exceptionally violent accretion process, likely fueled by a massive gas cloud or a star torn apart by tidal forces. After venturing too close to the black hole, the total energy released during this event exceeded the Sun's entire main sequence lifetime output by several orders of magnitude. Such immense energy output had profound effects on the environment at the center of the Milky Way. Fast forward to May 13, 2019. Astronomers using the Keck telescope observed more recent signs of activity. Sagittarius A** suddenly brightened in the infrared spectrum. Within just 2 hours, its luminosity increased to 75 times the normal level. This infrared flare lasted approximately 2 hours, with peak brightness surpassing even the brightest star in the galactic center. Such a rapid and intense brightness change confines the energy release region to an area very close to the event horizon. Observational data indicates that during this flare, the size of the radiating region did not exceed a few times the radius of the event horizon. This suggests we are observing physical processes near the innermost stable circular orbit of the black hole. Regarding the possible mechanisms behind this flare, astronomers have proposed several explanations. The most plausible involves magnetic reconnection processes releasing energy in the innermost layer of the accretion disk, similar to solar flares but on a vastly larger scale. Another possibility is that a small mass object, such as an asteroid or comet nucleus, was torn apart by tidal forces, with its fragments heated to extremely high temperatures as they fell into the black hole, producing a brief radiation burst. An intriguing hypothesis suggests the flare may have originated from hot spots within the accretion disk. These hot spots, formed by magnetohydrodynamic instabilities, produce the observed brightness variations due to relativistic focusing effects as they rotate around the black hole. Regardless of the specific mechanism, this flare event offers a unique opportunity to study the extreme physics of black holes. By analyzing the timescale and energy spectrum of the brightness variations, scientists can detect the degree of spacetime distortion near the event horizon. These occasional outbursts and flare events, though brief in duration, exert lasting effects on the environment. At the center of the Milky Way, intense X-ray and ultraviolet radiation can ionize gas within hundreds of light-years, altering the chemical state of the interstellar medium, influencing molecular cloud formation and evolution. High-energy radiation also heats interstellar gas, increasing its thermal pressure, thereby altering the gas's motion and potentially suppressing new star formation. This feedback mechanism plays a crucial role in galactic evolution. Relativistic particles produced during outbursts can be accelerated to extremely high energies. These cosmic rays interact with the interstellar medium as they propagate, producing diffuse gamma-ray radiation. During the outburst 200 years ago, the immense energy released may have also influenced the magnetic field structure in the galactic center, enhancing the turbulence of the magnetic field and altering its directional distribution. These transient active periods also provide us with a rare opportunity to study black hole feeding processes. During quiescent phases, the accretion process of black holes is too faint to allow detailed observation, while the enhanced radiation during outbursts allows us to glimpse the detailed physics of matter falling into the black hole. Notably, these outburst events may exhibit periodicity. Although current observational data is limited, theoretical models predict the galactic center black hole may undergo major outbursts every few thousand years. This periodicity may correlate with star formation activity in the galactic center or the motion patterns of molecular clouds. When massive amounts of matter migrate toward the galactic center under gravitational pull, migrates toward the galactic center, it triggers a new phase of black hole activity. Studies of historical outbursts and modern flares also help astronomers understand why Sagittarius A* remains so quiet most of the time. The answer may lie in the distribution characteristics of matter in the central region of the Milky Way. Compared to active galaxies, the interstellar matter density in our galactic center is lower, making it difficult for it to fall directly into the black hole. It must first lose angular momentum through some mechanism before entering an effective accretion process. Furthermore, the physical state of the black hole itself may also influence its activity level. For example, a slow rotation rate or specific magnetic field configurations can suppress the efficiency of matter accretion. Looking ahead, with the continuous advancement of observational technology, we will be able to monitor such outbursts and flare events more frequently, and may even capture the precise moment matter crosses the event horizon. These studies not only deepen our understanding of the galactic center black hole, but also provide crucial insights into the behavior of supermassive black holes in other galaxies. In the cosmic timeline, these fleeting outbursts resemble the murmurs of a colossal beast. Though ephemeral, they reveal the hidden true nature of this cosmic neighbor. According to Einstein's general theory of relativity, time is not uniformly flowing as described by Newtonian mechanics. The rate at which time passes is significantly influenced by the strength of gravitational fields. In strong gravitational fields, time actually slows down, This phenomenon is known as gravitational time dilation. To grasp this counterintuitive concept, we must begin with the fundamental geometry of spacetime. Einstein's revolutionary insight reinterpreted gravity as a geometric effect of spacetime curvature. Mass and energy warp the fabric of spacetime, while objects follow geodesic paths through this curved space. This geometric effect not only alters an object's trajectory, but also modulates the very rhythm of time's passage. The mathematical description of gravitational time dilation originates from the Schwarzschild solution, the exact solution in general relativity describing spacetime around spherically symmetric celestial bodies. This solution predicts that deeper within the gravitational potential, closer to the center of mass, clocks tick more slowly. Specifically, the ratio of time elapsed between two observers is determined by the difference in gravitational potential between their locations. A famous real-world application is the Global Positioning System. Atomic clocks aboard GPS satellites, situated within Earth's weaker gravitational field, run approximately 45 microseconds faster per day than clocks on the ground. Without relativistic calibration, the entire system would accumulate over 10 kilometers of positioning error within a single day. This vividly demonstrates that time dilation is not merely theoretical, but an observable physical reality. At the center of our Milky Way galaxy, this effect is particularly pronounced on the S2 star. The S2 star orbits Sagittarius A*, in a highly elliptical orbit, with a period of approximately 16 years. When it reaches its periastron, it comes within about 120 astronomical units of the black hole's center, reaching a speed of 2.7% of the speed of light. In this extreme gravitational environment, the clock on S2 runs noticeably slower than one on Earth. According to calculations based on general relativity, the time dilation effect peaks during S2's closest approach to the black hole, lasting several hours. For every million seconds elapsed on Earth, only about 999,999 seconds pass near S2. Though this minute difference may seem insignificant, modern astronomical observation techniques can detect this effect. Astronomers indirectly verified the existence of time dilation by analyzing the gravitational redshift of spectral lines from S2. As photons propagate from the intense gravitational field near the black hole to Earth's weaker gravitational field, they lose energy, causing their wavelengths to lengthen. Spectral lines shift toward the red end of the spectrum. This redshift directly reflects the magnitude of time dilation. The observational data aligns remarkably well with the predictions of general relativity. This provides strong support for Einstein's theory. When we turn our gaze toward the mysterious boundary known as the event horizon, the effect of time dilation reaches its extreme. The event horizon is a one-way membrane in spacetime, from which no matter or information can return once crossed. From an external observer's perspective, as an object approaches the event horizon, its passage of time slows progressively. As an object approaches the event horizon infinitely close, the time dilation factor approaches infinity. This implies that, to an external observer, the process of any object crossing the event horizon would require an infinite amount of time. The object appears frozen on the surface of the event horizon, its image rapidly fading to darkness due to extreme redshift until vanishing. This effect is sometimes termed the frozen star phenomenon. However, this description applies only to the external observer's reference frame. From the perspective of the astronaut falling into the black hole's own reference frame, the situation is entirely different. They will smoothly traverse the event horizon within a finite period of time, without perceiving any special boundary. This description dependent on the reference frame is precisely the ingenuity of general relativity. It reveals that the nature of spacetime is inextricably linked to the observer's state of motion. Time near the event horizon stretches infinitely, leading to profound issues like the information paradox. Information from objects falling into a black hole appears permanently trapped on the event horizon's surface. From an external perspective, this information takes an infinite amount of time to completely vanish. This phenomenon may conflict profoundly with quantum mechanics' unitarity principle. Research on the S2 star system and time dilation not only validates general relativity, but also provides clues for exploring quantum gravity theories. Near the event horizon, the spacetime singularity predicted by general relativity suggests that this theory must be unified with quantum mechanics. Time and space may exhibit entirely new discrete structures. At the Planck scale, by continuously monitoring the motion of stars like S2, astronomers are testing general relativity's predictions under strong gravitational fields. With unprecedented precision, any minute deviation from theoretical predictions may signal the dawn of new physics. This remarkable effect of gravitational time dilation is not only a triumphant victory for Einstein's theory, but also a vital window into the mysteries of the cosmos. Beneath the tranquil night sky, as we gaze toward the center of the Milky Way, we might imagine the distant star S2 performing its unique dance, whispering to us of spacetime's curvature and time's elasticity. Every note in this cosmic symphony deepens our understanding of nature's laws. According to Einstein's general theory of relativity, massive celestial bodies not only warp space, but also deflect the paths of light passing near them. This phenomenon is known as the gravitational lensing effect. Black holes push this effect to its extreme. When light from background stars or galaxies passes near a black hole, it travels along curved spacetime geodesics, forming multiple distorted images, and sometimes even presenting as Einstein rings. These ring-like structures represent a special case of gravitational lensing. The angle of light deflection depends on the black hole's mass and the closest distance between the light rays and the black hole. For supermassive black holes like Sagittarius A*, their gravitational lensing is powerful enough to produce observable distortions in celestial images. A unique region exists around black holes, known as the photon sphere. This spherical zone consists of unstable photon orbits, where photons can temporarily circle the black hole. For non-rotating black holes, the photon sphere's radius is 1.5 times the Schwarzschild radius. For Sagittarius A*, this distance is approximately 0.12 astronomical units. Photons within this region exist in a critical state. They may either fall into the event horizon or escape to infinity. Orbits within the photon sphere are unstable. Minor perturbations cause photons to either plunge into the black hole or flee into the distance. This instability produces intriguing optical effects. When matter passes near the photon sphere, it generates complex light curves. In the first image captured by the Event Horizon Telescope, the bright ring-like structure we observe is dominated by radiation near the photon sphere. This ring has a diameter of approximately 50 microarcseconds, highly consistent with the theoretically predicted size of the photon sphere. The formation of this ring structure can be understood as follows. Light originating from the accretion disk behind the black hole bends within the black hole's powerful gravitational field and ultimately bypass the black hole to reach our telescopes. These bent rays form a halo around the black hole. Due to the black hole's rotation and the Doppler effect, the brightness of this ring is not uniform across its different regions. The portion facing us appears brighter due to relativistic focusing effects, while the portion receding from us appears relatively dimmer. This asymmetry provides clues for studying the black hole's rotation. The dark region at the ring center is called the black hole shadow. It is not the event horizon itself, but rather the silhouette of the event horizon projected against the luminous background. Due to the extreme bending of light rays, the shadow's diameter appears larger than the actual event horizon. The size and shape of the black hole shadow contain rich information. By analyzing these features, we can test the predictions of general relativity and explore new physics beyond Einstein's theory. The trajectory of light propagation in strong gravitational fields requires solving the zero-geodesic equations. These equations describe the motion of photons in curved spacetime. Calculations show the black hole shadow is approximately circular, but exhibits slight deformation due to the black hole's rotation. Observations from the Event Horizon Telescope highly match these theoretical predictions. This not only confirms the validity of general relativity under strong field conditions, but also provides direct evidence for understanding the spacetime structure around black holes. Photons near the photon sphere require precise initial conditions to complete a full circular orbit. The vast majority of photons either rapidly fall into the event horizon or escape into the distant universe. Only a tiny fraction of photons that precisely meet the conditions can linger near the photon sphere for extended periods. This characteristic renders the photon sphere region an ideal laboratory for studying the physics of strong gravitational fields. By analyzing photons originating from this region, we can probe the most fundamental properties of spacetime. Gravitational lensing effects occur not only around black holes, but also around any massive celestial object. However, only near black holes does this effect manifest with such extreme and pure intensity. Understanding the patterns of this light bending is crucial for correctly interpreting black hole observational data. It helps us distinguish between genuine physical processes and visual illusions caused by gravitational lensing. With continuous advancements in observational technology, we will be able to study the properties of the photon sphere with greater precision. We may even observe the dynamic process of photons orbiting around black holes. This will open a new window for exploring the most extreme gravitational environments in the universe. Beneath the tranquil night sky, these bent rays silently traverse the cosmos, carrying information about the very fabric of spacetime, awaiting humanity's wisdom and instruments to decipher. Each observation is a profound dialogue with the universe. Every beam of light an unspoken poem of gravity. Tidal forces are fundamentally a gravitational gradient phenomenon. It originates from the uneven distribution of gravitational fields across space. When an object resides within a gravitational field, its different sections experience varying distances from the gravitational source, resulting in differing gravitational forces acting upon each part. This disparity in gravitational pull generates stretching or compressing effects. Consider the tidal forces between Earth and the Moon. The side of Earth facing the Moon experiences stronger gravitational pull, while the opposite side faces weaker gravitational force. This disparity causes the Earth to be slightly stretched toward the Moon, resulting in the familiar ocean tides we observe. In the extreme gravitational environment near a black hole, tidal forces exhibit even more astonishing effects. As an object approaches a black hole, the portion closer to the black hole experiences a stronger gravitational pull than the portion farther away. This gravitational disparity increases dramatically as the distance decreases. For stellar mass black holes, the event horizon radius is relatively small, meaning objects experience immense tidal forces long before reaching the event horizon. An astronaut just hundreds of kilometers from the black hole would already feel pronounced stretching effects, with gravitational differences between head and feet potentially reaching hundreds of times Earth's gravity. Such extreme tidal forces violently stretch objects, much like stretching a lump of dough into a long noodle. This process is termed spaghettification. During spaghettification, the object is stretched along the direction perpendicular to the gravitational field, while being compressed along the direction parallel to it, ultimately forming a long, thin structure. However, for supermassive black holes like Sagittarius A*, the situation is entirely different, due to their extremely large event horizon radii. Reaching tens of millions of kilometers, the tidal forces at the event horizon are relatively weak. An astronaut crossing the event horizon might barely feel the tidal forces' effect. This difference stems from the relationship between tidal forces and distance. They decrease inversely proportional to the cube of the distance, and inversely proportional to the square of the black hole's mass. For larger mass black holes, the event horizon radius is greater, so the tidal forces at the event horizon are actually weaker. Observing an object falling into a black hole from different reference frames yields entirely different descriptions. From an external observer's perspective, the object gradually decelerates as it approaches the event horizon, and ultimately appears frozen on its surface. The object's image rapidly dims due to extreme redshift. Simultaneously, under tidal forces, the object's dimensions perpendicular to its motion are compressed. This process is termed pancaking. Pancaking arises from gravitational time dilation. From the external observer's time coordinate, the object takes an infinitely long time to cross the event horizon. During this process, the leading and trailing edges of the object experience different time dilation rates, resulting in infinite compression along the object's direction of motion. However, from the object's own reference frame as it falls into the black hole, the situation is entirely different. The object crosses the event horizon within a finite time, and first undergoes spaghettification. After crossing the event horizon, it continues falling toward the singularity. During this descent, tidal forces steadily intensify until the object is completely torn apart. This reference frame-dependent description reveals a crucial property of general relativity. The nature of spacetime is intrinsically linked to an observer's state of motion. Descriptions of the same physical process can exhibit fundamental differences across distinct reference frames. For objects falling into stellar mass black holes, spaghettification occurs outside the event horizon, meaning external observers can witness the onset of this process. However, for supermassive black holes, spaghettification may occur inside the event horizon, rendering the process permanently invisible to external observers. Tidal forces affect not only objects falling into black holes, but also the interstellar environment surrounding them. When a star comes too close to a black hole, tidal forces may exceed the star's own gravitational pull, causing the star to be torn apart. This phenomenon is known as a tidal disruption event. During a tidal disruption event, stellar material is stretched into elongated streams. Some material falls into the black hole. Some material is ejected into interstellar space. This process generates intense electromagnetic radiation, serving as a crucial signal for studying black holes. Understanding the nature and effects of tidal forces not only deepens our knowledge of black hole physics, but also provides crucial insights into matter behavior within strong gravitational fields. In future observations, with advancing technology, we may directly detect gravitational wave signals from these extreme processes, thereby gaining deeper understanding of spacetime's essence. In the universe's extreme environments, Tidal forces act like an invisible sculptor, shaping matter's form in unique ways, revealing the infinite fascination of gravity, the fundamental interaction. According to the fundamental principles of quantum field theory, virtual particle pairs are constantly created and annihilated in the vacuum. These pairs typically annihilate each other within an extremely short time, without violating the law of energy conservation. However, near the event horizon of a black hole, the extreme curvature of spacetime alters this picture. When virtual particle pairs emerge near the event horizon, one particle may fall into the black hole, while the other escapes to infinity. This process requires energy extraction from the black hole's gravitational field, causing the black hole to lose mass. The escaping particle constitutes Hawking radiation. Hawking radiation exhibits perfect thermal spectral characteristics, meaning it appears to carry no information, being related solely to the black hole's mass, angular momentum, and charge, which aligns with the description of the no-hair theorem. However, when a black hole completely evaporates through Hawking radiation, a profound question arises. Where does the information carried by the original matter that fell into the black hole go? The fundamental principles of quantum mechanics require physical processes must preserve information integrity, and quantum states of information should remain traceable through unitary evolution. If information is indeed lost after a black hole evaporates, it would violate quantum mechanics' unitarity principle. This is the famous black hole information paradox. The information paradox challenges the foundations of modern physics, revealing a profound conflict between general relativity and quantum mechanics. In the extreme environment of black holes, if information is indeed lost, we must revise the fundamental framework of quantum mechanics. If information is preserved, we must understand how it is encoded in Hawking radiation. Hawking initially believed information was lost, a view that sparked decades of intense debate. However, based on recent advances in quantum gravity theory, most physicists now believe information is actually preserved, though encoded in Hawking radiation in an extremely complex manner. The holographic principle offers an elegant solution to the information paradox. This principle states that the information required to describe a region of space can be encoded on the boundary of that region. For black holes, all information that falls into a black hole is stored on the surface of the event horizon. When Hawking radiation occurs, this information is gradually released into the radiation. From the holographic principle's perspective, the interior of a black hole is essentially a holographic projection, with its entire information content stored on a two-dimensional surface. This description contradicts our everyday three-dimensional intuition, yet finds support in string theory and quantum gravity research. Another potential solution involves the properties of quantum entanglement. Particles from Hawking radiation maintain quantum entanglement with particles inside the black hole. As the black hole evaporates, this entanglement transmits information to the external radiation through complex mechanisms. Although individual radiation particles appear random, their correlations may encode complete information. In recent years, soft-hair theory in gravity has offered new insights. This theory posits that during evaporation, black holes retain certain extremely low-energy excited states. These states may carry information about the fallen matter. By studying the properties of these soft hairs, the information loss problem might be resolved. String theory describes black holes through the D-brane model. Within this framework, black holes are regarded as bound states of D-branes. Information is stored in the excited states of these D-branes. As the black hole evaporates, the information is preserved through interactions between the D-branes. From an observational standpoint, Verifying these theories presents significant challenges. Hawking radiation occurs at extremely low temperatures. For stellar mass black holes, as low as 1/1,000,000th of a Kelvin, and even lower for supermassive black holes. Direct detection is nearly impossible. However, by studying gravitational waves generated during black hole mergers, indirect evidence regarding information preservation may be obtained. In-depth exploration of the information paradox has spurred multiple significant advances in physics, including enhanced understanding of quantum gravity, new insights into the nature of spacetime, and revolutionary concepts like holographic duality. Within the framework of black hole thermodynamics, the information paradox also closely relates to thermodynamic laws. Should information truly vanish, it would violate the quantum version of the second law of thermodynamics. This connection further underscores the problem's significance. Notably, Hawking revised his stance in his later years, suggesting information might actually be preserved through some mechanism. This shift demonstrates the problem's complexity and depth, while reflecting the evolution of scientific understanding over time. Current research indicates preserving information during black hole evaporation may require fundamental revisions to our concept of spacetime. In certain theories, spacetime itself may be an emergent phenomenon, arising from more fundamental quantum entanglement structures. If this perspective holds true, resolving the information paradox will guide us toward a deeper understanding of reality's essence. Black holes, the most enigmatic celestial bodies in the universe, continue to challenge our imagination, pushing the frontiers of physics ever further. In exploring the information paradox, we are not merely solving a specific physics problem, but probing nature's most fundamental laws. Each theoretical breakthrough brings us closer to unveiling the universe's mysteries. Quantum entanglement, this peculiar quantum phenomenon, plays a pivotal role in black hole physics. When two particles become entangled, their quantum states become intimately linked. No matter the distance between them, a measurement on one particle will instantaneously affect the other. Near a black hole's event horizon, quantum effects become paramount. According to Hawking's calculations, black holes emit radiation through quantum processes, involving the creation of entangled particle pairs. One particle falls into the black hole, while the other escapes as Hawking radiation. The escaping Hawking radiation particle should remain entangled with its partner trapped inside the black hole, simultaneously to preserve information during black hole evaporation. Hawking radiation must also remain entangled with earlier radiation. This gives rise to a profound contradiction. Quantum mechanics prohibits a system from achieving maximum entanglement with two systems simultaneously. This fundamental principle, known as entanglement singlet, demands that Hawking radiation can only satisfy one of two entanglement states, and not both at the same time. This contradiction led to the firewall hypothesis, which proposes that at the event horizon, there may exist a high-energy region. Any object falling into a black hole would be instantly annihilated upon crossing the event horizon. This high-energy zone is termed the firewall. The firewall hypothesis directly challenges Einstein's equivalence principle, a cornerstone of general relativity. It states that within a local region, gravitational fields are indistinguishable from accelerated reference frames. A freely falling observer would perceive no gravitational effects. If firewalls truly exist, it implies the equivalence principle is violated at the quantum level. A free-falling observer would encounter a devastating wall of high-energy particles at the event horizon, rather than smoothly traversing it. From an external observer's perspective, firewalls may be essential to resolving the information paradox by breaking the entanglement between falling particles and Hawking radiation, thus preserving quantum mechanics integrity. But this solution comes at a high cost. It overturns our understanding of space-time continuity. However, many physicists remain skeptical of the firewall hypothesis, as it introduces new theoretical difficulties. If the event horizon truly constitutes a physical boundary, the concept of spacetime within black holes must be reevaluated. The smooth spacetime continuum of general relativity may no longer hold at the quantum gravity level. This paradox compels physicists to delve deeper into potential forms of quantum gravity theory. String theory offers an intriguing perspective. Within its framework, black holes are viewed as collections of D-branes. Information is stored in the excited states of these D-branes. Physical processes at the event horizon can be described through the interactions of these D-branes. Loop quantum gravity theory proposes that spacetime itself possesses a discrete microscopic structure. At the Planck scale, spacetime is composed of a spin network. This discreteness may naturally resolve the firewall paradox. Another possibility is that entanglement itself may be more complex than we imagine. Perhaps some quantum process exists, capable of reconciling seemingly contradictory entanglement requirements without invoking a destructive firewall. Recent research indicates a more refined description of black hole evaporation may automatically resolve this paradox. As the black hole evaporation process progresses, the geometric structure near the event horizon undergoes changes. This dynamic evolution may prevent the formation of a firewall. Research into this paradox profoundly influences our understanding of quantum gravity. It reveals that at the Planck scale, the concept of spacetime may require fundamental revision. Quantum entanglement may not merely be a phenomenon within spacetime, but could be the very foundation from which spacetime itself emerges. From a broader perspective, the firewall paradox represents a core challenge facing modern physics: how to reconcile general relativity with quantum mechanics, how to understand the nature of spacetime, how to explain the fate of information. These questions converge within this paradox. Every exploration of such fundamental questions, regardless of the ultimate answer, propels us toward deeper natural laws. At the intersection of quantum and gravity lie the universe's deepest secrets, awaiting our discovery. Within the mathematical framework of general relativity, singularities represent regions where spacetime curvature approaches infinity. At this point, all known physical laws cease to hold. Density and temperature reach infinite values. This mathematical divergence signals the theory's inherent limitations. The emergence of singularities is no accident. It is the inevitable outcome of Einstein's field equations under extreme conditions. The singularity theorems proven by Penrose and Hawking state, under fairly general conditions, singularities must appear in spacetime. This theorem reveals the inherent limitations of general relativity when describing the beginning of the universe and the interior of black holes. At singularities, not only do physical quantities become infinite, the causal structure itself is destroyed. The concept of time loses meaning here. Spatial dimensions no longer possess clear definitions. The familiar notion of continuous spacetime completely collapses within this extreme region. Faced with this fundamental challenge, physicists have developed various quantum gravity theories, attempting to resolve the singularity problem. The fundamental premise underlying these theories is that, at the Planck scale, spacetime itself should exhibit quantum properties. String theory offers a compelling solution. In this framework, fundamental entities are not point particles, but one-dimensional vibrating strings. These strings have characteristic lengths near the Planck length. When matter is compressed to extreme densities, the extensional nature of strings can prevent infinities. Within the string theory framework, true singularities may not exist inside black holes. Instead, a structure called a string star may prevail, where vibrational modes of strings maintain a stable, high-energy state. This state, though extremely dense, preserves finite values for all physical quantities. Loop quantum gravity takes a different approach. This theory avoids singularities by quantizing spacetime itself. In loop quantum gravity, space consists of discrete, quantized areas and volumes. The existence of these fundamental units sets a natural lower bound for matter compression. According to loop quantum gravity calculations, when matter is compressed to a critical density, gravity naturally transforms into a repulsive force. This repulsive effect prevents singularities from forming. Instead, a cosmic rebound process occurs. Through this mechanism, the interior of a black hole may connect to another region of spacetime. Causal set theory proposes a more radical concept. This theory posits that spacetime is fundamentally discontinuous, composed of basic causal events. Within this framework, the singularity problem vanishes automatically, as continuous spacetime itself becomes merely an approximate description. Other theoretical attempts exist, such as torsion theory, which reinterprets spacetime through complex geometry, seeking to fundamentally reshape our understanding of spacetime. Within these novel mathematical frameworks, singularities may prove to be artifacts of coordinate choice, rather than genuine physical entities. Though these quantum gravity theories differ in mathematical form, they all converge on a shared insight. At the Planck scale, spacetime may exhibit a discrete, foam-like structure. This concept of quantum foam was first proposed by Wheeler in the 1950s. Fluctuations within this quantum foam may prevent singularities from forming. When matter is compressed to extreme states, quantum effects begin to dominate physical processes, generating effective pressure to counteract gravitational collapse. The interior of a black hole may not contain a true singularity, but rather a region of extreme density and energy, where quantum gravitational effects fundamentally alter the laws of physics. This region may connect to other universes, or other parts of our own universe, forming a complex multiverse structure. Recent studies suggest the singularity problem may be closely tied to the information paradox. If singularities are indeed eliminated by quantum gravity effects, then information falling into a black hole might be preserved through some mechanism, rather than being lost forever within the singularity. In-depth exploration of the singularity problem not only concerns our understanding of black hole interiors, but also touches upon the ultimate question of cosmic origins. The Big Bang itself represents a singularity on a cosmic scale. Resolving the singularity problem may ultimately reveal the mystery of where the universe came from. Although a complete quantum gravity theory remains elusive, these explorations have profoundly enriched our understanding of spacetime's essence. Each theoretical advancement brings us closer to comprehending how nature operates at the most fundamental scale. Future research, with higher precision gravitational wave observations, may provide crucial tests for these theories. By analyzing the final stages of black hole mergers, we might glimpse the physical laws governing the vicinity of the singularity. The enigma of the singularity represents the frontier of contemporary physics. Beyond this boundary lie nature's deepest secrets, awaiting humanity's wisdom and courage to explore. Observational data indicates that supermassive black holes exist at the centers of nearly all massive galaxies. The masses of these black holes exhibit a striking positive correlation with the bulge mass of their host galaxies. This discovery is known as the M-sigma relation. The M-sigma relation indicates that black hole masses account for approximately 0.1% to 0.3% of their host galaxy's bulge mass. This proportional relationship holds across multiple orders of magnitude, from smaller black holes of millions of solar masses to cosmic behemoths of billions of solar masses, all strictly adhering to this law. This strongly suggests a profound coevolutionary history between black holes and galaxies. Sagittarius A*, the central black hole of the Milky Way, perfectly aligns with this cosmic law. Its mass is approximately 4.3 million solar masses, while the Milky Way's bulge mass is about 10 billion solar masses, falling precisely within the range predicted by the M-sigma relation. This precise correspondence indicates that black holes are not passive residents at galactic centers, but actively participate in the galaxy's formation process. Through so-called feedback mechanisms, black holes regulate star formation within galaxies. When actively accreting matter, black holes release immense energy. This energy, in the form of radiation and outflows, influences the entire galactic environment. During early stages of galaxy evolution, black holes may suppress star formation via intense radiation feedback. High-energy photons heat galactic gas, increasing its thermal pressure, making it difficult for the gas to cool and collapse into new stars. This self-regulating mechanism ensures galaxies do not grow too rapidly. Beyond radiative feedback, black holes also generate powerful outflows of matter. When the energy released during accretion becomes sufficiently large, it expels vast quantities of gas from the galaxy. This expelled gas, which would otherwise serve as raw material for star formation, directly reduces the galaxy's efficiency in producing new stars. Throughout the Milky Way's evolutionary history, Sagittarius A** likely underwent multiple active phases. During these periods, it shaped the galaxy's structure through feedback mechanisms. Though now in a relatively quiescent state, this past activity has left permanent imprints in the Milky Way's chemical composition and stellar distribution. The gravitational influence of Sagittarius A* directly determines the structure of the galactic center. Within a range of several light-years from the black hole, the distribution of stars exhibits a distinctive nuclear ball morphology. This structure arises partly from the black hole's gravity, which shapes stellar orbits over long timescales. The black hole's tidal forces also influence the evolution of molecular clouds at the galactic center. When gas clouds approach too close to the black hole, they are torn apart by tidal forces. This process provides fuel for the black hole, while simultaneously preventing the formation of massive star clusters. The maintenance of the Milky Way's spiral arm structure may also be linked to the central black hole. Gravitational perturbations from the black hole generate density waves within the galactic disk. These density waves, like ripples in the cosmic ocean, guide the distribution of stars and gas, shaping the spiral arm patterns we observe. Compared to galaxies harboring more active black holes, the Milky Way currently exists in a state of relative equilibrium. Sagittarius A*''s moderate mass and low activity level allow the Milky Way to sustain continuous star formation without depleting its gas reserves excessively. This equilibrium may not be eternal. When the Milky Way collides with the Andromeda Galaxy in the future, Sagittarius A** could be reactivated. During the collision, vast amounts of gas will be transported to the galactic center, providing abundant fuel for the black hole and triggering a new phase of intense activity. From a broader perspective, Sagittarius A* serves as the gravitational anchor, not only sustaining the galaxy's overall structure, but also regulating its evolutionary rhythm through intricate feedback loops. Like a cosmic architect, it meticulously shapes our stellar system with its invisible gravitational hand. Understanding this symbiotic relationship between black holes and galaxies stands as one of contemporary astrophysics' central challenges. Each new observation of the Milky Way's core reveals fresh details of this cosmic dialogue. On this tranquil night, as we gaze upon the stars, we may sense the profound influence of this distant cosmic neighbor. In approximately 4 billion years, our Milky Way will begin a cosmic dance with the Andromeda Galaxy. These two massive spiral galaxies will gradually draw closer under gravitational pull, initiating a merger process spanning billions of years. As the galaxies begin to intertwine, their stars will not collide directly, due to the vast distances between them. However, interstellar gas and dust clouds will collide violently, triggering a spectacular burst of star formation. In this cosmic merger, massive amounts of gas will be gravitationally driven toward the central regions of both galaxies, providing unprecedented fuel to the supermassive black holes at the cores of Sagittarius A* and Andromeda. As gas continues to pour in, Sagittarius A* will awaken from its current dormant state, transforming into a dazzling quasar, emitting light millions of times brighter than today. The two supermassive black holes will begin orbiting each other, forming a binary black hole system at the galaxy's core. Their gravitational interaction will fling nearby stars out at extreme velocities, creating hypervelocity stars. After hundreds of millions of years of orbital decay, these two black holes will eventually merge into a larger black hole. This merger will generate powerful gravitational waves, propagating through space-time. Yet for life on Earth, this process will unfold in complete silence. The mass of the newly merged black hole will reach tens of millions of solar masses. It will become the gravitational center of the newly formed Andromeda Milky Way galaxy. Yet this is merely the beginning of the story. On a timescale of trillions of years, stars will gradually exhaust their nuclear fuel. White dwarfs will cool and dim, neutron stars will cease pulsing, and the universe will enter a dark age. In this distant future, black holes will become the dominant celestial bodies in the cosmos. They will continue to grow slowly, by devouring the remaining interstellar matter, and occasionally capturing stellar remnants. Yet even these formidable cosmic entities cannot evade their ultimate fate. According to Hawking's revolutionary discovery, black holes gradually lose mass through quantum effects. This process is known as Hawking radiation. The mechanism behind Hawking radiation originates from quantum fluctuations near the event horizon, where virtual particle pairs continuously emerge and annihilate. When this occurs near the event horizon, one particle may fall into the black hole, while the other escapes into the cosmos, carrying away a tiny fraction of the black hole's energy. For supermassive black holes like Sagittarius A*, the temperature of Hawking radiation is extremely low, just 10⁻⁻1 degrees above absolute zero. This means they evaporate at an incredibly slow rate. The time required for Sagittarius A* to completely evaporate reaches 10 to the power of 97 years. This number is so immense that writing it out in full would exceed the total number of atoms in our entire universe. For most of the evaporation process, the black hole remains virtually unchanged until its final stage, when the black hole's mass shrinks to approximately 10 to the power of 12 kilograms. The intensity of Hawking radiation begins to increase significantly. In its final moments, the black hole will end its existence in a violent explosion, converting all its accumulated mass into energy. The energy released by this explosion equals the energy of millions of tons of matter completely converted. With the disappearance of the last black hole, the universe will enter its final phase, leaving only sparse fundamental particles, drifting through an ever-expanding space. Photons will continue to redshift, their wavelengths stretch to cosmic scales, until they scarcely interact with other particles. The once vibrant universe will become cold and dark, with temperatures approaching absolute zero, and density tending towards zero. All structures will dissipate, and all energy gradients will be smoothed out. In this ultimate future, time itself may lose meaning, as no discernible changes mark its passage. The universe will reach maximum entropy, and all processes will cease. Yet this may not be the true end. Some theoretical physicists speculate that, on extremely long timescales, quantum fluctuations might accidentally trigger the birth of new universes, or our universe could be merely a part of a larger cosmic landscape. But from our human timescale, these processes are unimaginably distant. The era in which we exist coincides with the universe's most dynamic period. Stars blaze, galaxies whirl, life proliferates. When we gaze upon the night sky and look toward the center of the Milky Way, where Sagittarius A resides, we see not only a cosmic monster, but also a character in the universe's long evolutionary tale. It has shaped our galaxy over billions of years, and will quietly fade away in an even more distant future. This realization makes us feel small, yet also cherish every moment of the present. In this vast cosmic drama, we are both spectators and participants. Through scientific exploration, we glimpse the universe's past and future, understanding our place within it. Now relax your mind. Let these reflections on eternity and fleeting moments carry you into peaceful slumber. Sleep soundly within this boundless cosmos. The discovery and study of Sagittarius A** reveal a profound truth. Even the most extreme phenomena in the cosmos obey elegant, unified natural laws. This colossal beast lurking at the Milky Way's core governs hundreds of billions of stars with its immense gravity, yet simultaneously exhibits astonishingly gentle traits. Its existence demonstrates nature's delicate balance between destruction and creation. By studying this cosmic monster, we not only deepen our understanding of black holes themselves, but also advance our knowledge of spacetime gravity and the nature of matter. Each accumulation of observational data, each refinement of theoretical models, brings us closer to a complete cosmic portrait. The allure of scientific exploration lies in its demand for rigorous empirical inquiry, and its reliance on creative theoretical frameworks. As we pioneer the frontiers of intellect, we often discover unexpected beauty. The precise orbits of stars around Sagittarius A* function like a meticulously designed cosmic clock. Each stellar trajectory narrates a tale of gravity. These celestial motions obey the same physical laws governing objects on Earth. The shadow of a black hole captured by the Event Horizon Telescope not only validates Einstein's predictions, but also reveals to us the perfect unity of geometry and physics in nature. The interplay of light and shadow within that ring-like structure has become a classic symbol of scientific beauty. The quiet and active cycles of a black hole can be likened to the rhythmic breathing of the universe. During its long dormant periods, It silently sustains the stability of the galaxy. During its brief moments of awakening, it unleashes immense energy to reshape its surroundings. This alternating rhythm of stillness and motion evokes many phenomena in nature, from the cycle of seasons to the rhythms of life. Across different scales, the universe displays similar cyclical patterns. The current quiet phase of Sagittarius A* offers a unique research opportunity. During this relatively mild period, we can meticulously observe the fundamental properties of the black hole, without interference from intense radiation. The whispers of this cosmic colossus, translated through sophisticated instruments, become vital information for our cosmic understanding. Each data acquisition feels like a dialogue with the universe. The journey of scientific progress teaches us that behind every seemingly terrifying natural phenomenon lies profound underlying order. When we explore with rational eyes, fear often transforms into awe and curiosity. The study of Sagittarius A* also reminds us of humanity's insignificance and grandeur within the cosmos. Our insignificance lies in being no more than a speck of dust suspended in infinite void. Our grandeur lies in our capacity to comprehend these distant cosmic wonders. In this era of information explosion, scientific exploration offers us a perspective that transcends mundane trivialities. It allows us to touch eternal mysteries and experience the boundless freedom of thought. The quest to unravel cosmic laws not only quenches our thirst for knowledge, but also enriches our spiritual world. As we comprehend nature, we also come to understand ourselves. Now let us gently shift our focus from the distant heart of the Milky Way back to the present moment. Feel the rhythm of your breath. Experience the relaxation of your body. Imagine the starlight orbiting the black hole, transforming into gentle points of light, scattering around you, bringing tranquility and peace. The laws of the universe are harmonious and unified, like an eternal symphony. On this tranquil night, let it accompany you into peaceful slumber. With each breath, allow your body's tension to gradually release. Let your thoughts drift freely like starlight. In the embrace of the cosmos, you can relax completely, sleep soundly. Let the beasts whisper become the backdrop of your dreams, guiding you into sweet sleep. Now, let us slowly draw our thoughts back from the distant center of the Milky Way. Feel every point where your body touches the bed. Notice how your breath flows naturally in and out of your body. Imagine that giant beast slumbering at the heart of the Milky Way. With its steady gravitational field, it safeguards the entire galaxy, just as it safeguards your peace at this very moment. Let all knowledge of black holes and galaxies fade gently like faint starlight in the night sky. No need to deliberately remember complex scientific concepts. Simply feel this tranquility connected to the cosmos. With each breath you take, you resonate in harmony with this vast universe, like the slow dance of stars within a galaxy, carrying a natural and elegant rhythm. Feel your eyelids growing heavy, like nightfall gently enveloping the earth. Release your weariness with each exhalation. Imagine yourself floating in the tranquil cosmos, gently cradled by soft starlight. That immense presence at the Milky Way's core, though possessing staggering energy, now stands as a silent guardian. 26,000 light-years away, it maintains the cosmos's order and balance for you. In this infinitely vast universe, your very existence is a miracle. Now let this realization bring you profound peace. With each breath, allow your body to relax deeper. Let your thoughts grow calmer, like cosmic dust settling gently. Find your own peaceful resting place. The stars will continue their eternal dance. The black hole will remain in slumber, and you may drift peacefully into dreams. In this boundless cosmos, may your sleep be as deep as interstellar space. May your dreams be as brilliant as nebulae. Good night, dear stargazer. Good night, Milky Way. May the universe's tranquility dwell within your heart.